Uh, my name is Carlos Lisboa, and I am HVAC designer and consultant for over 25 years. I look a little bit younger than I am. And in 2010, I was honored to be invited for the first joint technical committee between ASHRAE and REHVA. And it was a privilege to be part of this group, which John Bullen was a part too, as a REHVA representative. And there was a 5-year work that ended with the publishing of this book, the first book that was published together between ASHRAE, the American Association, and REHVA, the European Federation. This was the old book that REHVA published in 2004, and at 2010 ASHRAE had the intention to draft its own guide, and REHVA asked ASHRAE to publish a joint guidebook so that there would be just one book for the industry that would be consistent, updated from 2004, and benefiting from the range of experience from both continents. And the first meeting was held in 2010, actually in Stockholm. The committee was composed of 6 consultants, 3 from Europe, 3 from the United States, 7 manufacturers. There were 10 face-to-face meetings, lots of teleconference meetings. One of these meetings was held here in Tallinn, I believe 4 years ago. And finally, the work was submitted to ASHRAE and REHVA and finally published in January 2015. These were the guys that worked in this book. I would say it was a very enjoyable experience to work with all these guys from both continents, and we had also a good time. It was not just plain work. Now let's start with the technology and with the concept of an active beam. In an active beam, primary air is supplied to the beam plenum, and room air, air is supplied through jet nozzles, inducing air, and for one part of primary air, between 2 to 5 parts of secondary air from the room are induced and forced through a water coil. This water coil can cool or heat the air. Finally, the mixing of primary air and secondary heated or cooled air is supplied to the room through an air diffuser. This is the active beam concept. So we can move a lot of air without using a fan or with a motor, just using pressure in the beam plenum. There are lots of different active beam designs. This is the exposed installation without a ceiling, a suspended ceiling. This is the recessed installation, which is the most often used solution. We also have under the window sill installation, and also 4-way beams, hotel room, underfloor, etc., etc. The passive beam concept. In a passive beam, we don't have primary air. We just have a coil, and the passive beam just cools. It can't heat. It just cools the air. We have a coil and a box, a shroud. And actually, what makes the air move through the coil are buoyancy forces. Cool air has a higher density and drops down. And so it's the stack effect that makes the movement of the air. And this graph shows that the higher the shroud, the higher the stack effect, and so the higher the beam capacity. There are also different designs of passive beams, the recessed installation, the exposed installation. And now this slide shows us the whole system, not just the beams, but the air handling unit, the beams, the water distribution, the heating and cooling system. And there are functions that are performed by the beam itself in the rooms. There are other functions that are performed by the primary air. The beam actually has these functions. It cools the room, just sensible cooling, because actually there is no condensation in the beam coil, so it's just sensible cooling. Also, it can also heat the room and promote a room air distribution. The primary air functions are ventilation, it supplies ventilation air, take care of ventilation loads, and also, this is a very important function, it takes care of latent load in the room. So all dehumidification is taken care by the central primary air handling unit. Also, finally, primary air, since it is supplied at a temperature that is under the room air temperature, also provides some sensible cooling. But it should be small, a small part of the room sensible cooling. Typically, a passive beam can deliver up to 150 watts per linear meter. Active beams typically can deliver up to 180 watts per square meter. Chilled water is typically between 14 and 18. This should be above indoor air dew point. Hot water between 30 to 45. Primary air temperature between 30 to 21. Beam plenum pressure between 50 to 250. Of course, it's much better to have 50 than 250. This criteria, room sensible cooling by chilled water in the beam should be over 60%. We'll go further on these issues later on next slides. And typically also, this is a very specific issue of this system, there are non-condensing coils at the room level. So a condensation prevention strategy is required. We must not allow to have condensation at the room coils. The energy benefits of a beam system are maximized whenever we use it in moderate room sensible loads under 100 watt per square meter. Moderate room latent load. Remember that all the latent load is taken care by the primary air. So if we have a high latent load, we need lots of primary air. Low air side load fraction, I will explain better in further slides what this means. But actually, I can at the moment just say that if you need a lot of primary air to cool the room because you have a high sensible cooling load, and if you have over 60-50% percentage of cooling done by primary air, maybe you shouldn't use a beam. Maybe you should use other kind of systems. But we'll go in further on this issue on next slides. Beam systems can be applied to all kinds of applications, but they are not well suited for places where you have high humidity loads and where they are difficult to control, or places with very high loads. For instance, areas of ingress or egress of buildings in which there are open doors and lots of humidity coming from the outside to the indoor. Leaky buildings, in old buildings with bad windows in which lots of infiltration occurs and it's difficult to control indoor air dew point. Also auditoriums, okay. This type of applications are not the best for beam systems. This is an example of a recessed installation. This is an example of exposed beam with integrated lighting. This is an example of a beam applied to a hotel room. You see that the beam actually is installed in a very similar way as a fan coil. And also laboratory applications, you see the beams here. So, for the designer, the specificity of the beam system is that we must do a primary airflow calculation taking in account dehumidification. And so, in a beam system, primary airflow has the following functions and corresponding requirements. Ventilation is the first function of the primary air, and the goal is to achieve comfort and health, and we have to comply with local codes or the owner project requirements. Indoor air dehumidification for comfort, but very important for condensation control. And the criteria is that indoor air dew point must be equal or under water temperature supplied to the beams in order to avoid condensation. And there is a third function, which is space cooling. As I mentioned, since the primary air is usually at a lower temperature than room air, it also provides some space-sensible cooling. And this is the third function. And in order to get indoor air temperature inside the comfort range. The primary airflow is the highest of the three. We must first calculate the required primary air for ventilation, calculate after what's the required primary airflow for dehumidification, and finally this last one is done at the end with the manufacturer software of the beams. In order to select the beams, we will usually get, in some cases, we have the need to increase the primary airflow above the required for dehumidification. So the primary air to the beam is the higher of the three calculated primary airs. Of course, the best would be that the primary air would be just the required for ventilation. And you will see in the next slide that here in Europe it is often so. This slide shows the difference between ventilation requirements according to the European standard and to ASHRAE 62.1. And you see that you can check it later, or the calculation is explained in these tables. For an office space with just one person with 16.5 square meters. The required primary air according to European standard is 19 liters per second. But according to ASHRAE 62.1, it's just 7.4. It's a very big difference. I would say I just had the difference lays on the issue that the European standard was worked out in order to satisfy visitors to the spaces. A person that at the moment it enters the room, when the American standard was done to satisfy occupants of the space. An occupant is a person that has been for over 15 minutes inside the room, and so his olfactory, his nose is adapted to the others of the room, and so he is satisfied with the lower amount of primary air, of ventilation air. That's the main reason why these two standards go to very different values. As a conclusion regarding ventilation, in Europe, when you calculate airflow according to the European standard, you get a high airflow, and usually this ventilation airflow is enough to dehumidify. In the States, it's not enough. So you have to increase primary air above the ventilation requirements. Also, this is very important because designers must be aware that this calculation has some safety factors associated with the calculation, because in order to calculate primary air for dehumidification, we consider steady state conditions. We are not considering dynamic effects or water vapor absorption by walls, furniture, and so on. So we are making a conservative calculation in what regards primary air flow required for dehumidification. As I mentioned before, in some cases of high sensible loads, when we go to the point in which we are selecting the beams, we have calculated the requirements for ventilation, the requirements for dehumidification, and we are selecting the beam, and we go with the manufacturers to select the beams, and we get to the conclusion that we must increase primary air in order to get to the required sensible load. We should bear in mind that if we have over 40% cooling, sensible cooling done by air, we are not taking full benefit of a chill beam system. And we should think about solutions to minimize this energy consumption associated with air. So we should be able to design a system that can vary the amount of primary air, either using a separate boost diffuser when the room is fully occupied, or use VAV beams, or beams that can deal with different amounts of primary air. Now, regarding the control of the system, there are these types of control. We have zone control, we have chill beam supply water temperature control, we have primary air conditioning control, and condensation prevention. In what regards zone control, primary air control of space temperature is usually accomplished by modulating the water flow while keeping the primary air constant. Of course, we should always try to use demand control ventilation and try to implement beam systems with variable primary air. This will minimize significantly energy consumption of the HVAC system. It's very important to have a very accurate control of the temperature of the water that is supplied to the beams in order to avoid condensation. And when I say an accurate control, is a very stable control. If you have a system that supplies 14 degrees or 16 degrees, doesn't supply between 10 and 20 degrees. Because if you have big oscillations of water temperature, you have risk of condensation when you have these low water temperatures. Unfortunately, is often in existing systems that this control doesn't work properly, doesn't have a very stable temperature supplied to the beams. This is very important. The most often used solution is to have a three-way mixing valve that that controls the temperature that is supplied to the beams. And we have a secondary pump that supplies water to the beams between the temperatures that are required to cool the space, avoiding condensation, always being above dew point, indoor air dew point. This is the solution when we have a primary water temperature of around 7 degrees, for instance. It's usual, and there is a mix of this low primary water temperature with return water temperature in order to have a higher temperature to the beams. This second solution is not so often used. I prefer this one because you can have a much better quality control of the temperature with a two-way valve than with a three-way valve. This is hydraulically basically the same. Instead of a three-way valve, we have a two-way valve and a bypass. And also, it can be done this way with a heat exchanger and a separate hydraulic system for the beams and another hydraulic system for the primary water system. The best, of course, would be to use neither of these three solutions, but to use dedicated chillers to the beams producing this higher temperature water. Because a chiller producing a higher temperature water will have a much higher efficiency. Of course, the designer has to calculate the cost and benefit of this solution. Now on primary air conditioning control. I said before that in a beam system, primary air has the function, a very important function, to control humidity and avoid condensation. And so it's paramount to have a very good control in the air handling unit. So, besides controlling supplier temperature, the primary air handling unit should control primary air dew point or specific humidity. When we design the system, we consider a certain dew point for the primary air and a certain amount of humidity in the primary air. And this is based on this value that we do the dehumidification calculation. So the primary air handling unit should control this indoor supplier dew point so that it is never above the design value. Also on condensation, which is one of the specific issues of this kind of systems. Another fact that brings some safety to our calculation, I mentioned before the issue of dynamic effects that are not considered in the calculation. Normally, we just make a steady state water mass balance. Also, there is another issue that brings some safety to the calculation, because recent investigation shows that it's not so easy to put a beam to force a beam to have falling droplets of water. Actually, in lab tests in which conditions were created to have condensation on the beams, more than lots of tests were done, and the first visible droplet in the water pipe supplying to the beam was seen when we had about, I said we, but I wasn't actually in part of this, I just read the results. Only when we had 2 degrees Celsius under dew point, the first droplet was detected. Of course, whenever the water temperature is under dew point, there will be condensation. That's psychrometrics, that's physics. But it's little condensation. It sweats, but it doesn't have enough condensation to develop a big water and drop to fall, to have enough mass to fall and rain. Okay, so actually the first big droplet was seen when the water temperature was 2 degrees Celsius under dew point. So there is also some safety margin, because we calculate dehumidification for indoor air dew point, and not under indoor air dew point. If the design is correct, and the installation and the system is correctly installed and commissioned, there's no way you can have condensation in the beams. You will not have condensation in the beams. If you supply an adequate amount of correctly conditioned primary air, and you have a good control of the chilled water to the beams, and also important, at morning startup, first turn on the air handling unit, and only after some time, when we have a lower indoor air dew point, start supplying chilled water to the beams. If we do everything right, there will be no issue, no problems. If the design is right, if the construction is right, there can be no condensation. It's not physically possible to have condensation. However, sometimes things are not right, either in design or in construction or commissioning. So we need prevention systems in case condensation may occur. And so safety condensation prevention can consist on reactive strategies or proactive strategies. This is the easiest way to do and cheapest way. Install condensate detectors that will stop water supply to the beams and can also increase chill water temperature set point to the beams. This is a very cheap solution. It's just an equipment, well, it's just two wires that are attached to the pipe. If there is water in the pipe, it's established the connection between the two wires. and the system detects that there is condensation in the pipe. This is very cheap, very simple and effective way to detect condensation, and using this you will not have falling drops in the beams. Of course, condensation will happen, as I mentioned before, if something goes wrong in design or in construction. But this will avoid the falling droplets, and the control system can automatically correct conditions so that there will be no falling droplets. Anyway, if this happens, a message should be sent to maintenance to correct. It shouldn't happen. Okay, this is a safety measure. It's not supposed to happen. Also, as a proactive strategy, a window switch, whenever you have buildings with openable windows, whenever a person opens the window, the chill water to the beams should be shut down. Of course, this is to prevent condensation, but not just for that. Any kind of system, of air conditioning system, whenever the occupant opens the window, any kind of system should be shut down, because we don't want to condition outdoor air, the city. We want to condition the building. It makes no sense, energy-wise, to have an air conditioning system working with open windows. So this is not specific to chill beams, but it's also important regarding condensation. Of course, in other systems, if you open a window, you are just wasting energy. In chill beam systems, besides wasting energy, you may have some droplets if you are opening the window in a climate which is humid and you have outdoor air dew point under the chill water temperature that's supplied to the building. Above, I'm sorry. Also, this is another solution that actually I don't use this, but in the States many designers use this, monitoring indoor air dew point and resetting chill water set point above the measured indoor air dew point. This is good. This is expensive. It's an expensive solution to have indoor air dew point monitoring everywhere. Now on energy analysis. One of the advantages that is mentioned on beam systems is that they are very energy efficient. Okay, it's the job of the energy designer to evaluate that. And in order to do that, you should use a dynamic building energy simulation software, like Energy Plus or EDICE, or whatever. But the person that uses this software that will evaluate the energy performance of the system must fully know and understand the technology to be simulated, and also understand the calculation method used in the software. This is tough, but and sometimes requires a teamwork. Most of the times, these two knowledges are not in the same person. There is one person that has a full knowledge of the software, and another person that has the full knowledge of the technology. Whenever this is the case, these two persons should work together. And what are the features in a beam system that reduce energy consumption? And also, there is also a feature that increases energy consumption. You see for the space left that more features reduce energy than those that increase energy consumption. Well, when we use higher chill water temperature, we have a potential to reduce energy consumption. I will go further on each one of these in the next slides. Also, we can use a lower hot water temperature. We use water to transport thermal energy. This is also a very important feature. We do not do excessive and uncontrolled humidification. And we have energy efficient room air distribution. I will go on the next slides more in deep on these issues, but I will just, on this one, efficient room air distribution, I will just explain it now, quickly. What do we mean by this? If, for instance, you are comparing a beam with a fan coil, air distribution in the room in a fan coil is promoted by a fan that's installed inside the fan coil. This is naturally a small fan with a small motor. And as you know, small fans have lower efficiency than big fans. That's physics, just physics. There's no way you can go around this fact. Also, a small motor is less efficient than a big motor. That's also physics. So, when you have a fan coil, you have all this recirculating air that is moving with a small fan and a small motor, okay? When you have an active beam, as you saw in the first slide, all this room air circulation is promoted by the pressure in the beam plenum, not by a small fan and a small motor. And this pressure was created in the primary air handling unit, which is big, and you can have there a much bigger fan and a bigger motor. That's the reason why we say that we have energy efficient room air distribution. Actually, if any of you is doing this energy simulation with either ICE or Energy Plus, whatever, you have to input in some part of the input what's the efficiency of the fan. Okay? If you are using primary, if you are using chill beams, you can input the higher efficiency. You can input 70%, 75% efficiency. Or in the motor you can input 90% efficiency. But if you are using a fan coil, no way. You'll never have above 50% efficiency in the fan, not above 70% efficiency in the motor. And that will affect the energy calculation. And that's one issue. This is one example of the knowledge that the energy expert should know about the technology. There's no way you can have a fan coil with a 70% efficiency in the fan, neither in a 90% efficiency in the motor. Anyway, also, we have a feature that increases energy consumption in beam systems, because in order to avoid condensation we need higher chill water to the beams, and since we have a higher chill water we need a lower delta T. Usually chill water temperature to the beams is designed to have a delta T of just 2 degrees Celsius. In a fan coil or all other kinds of hydronic systems, the delta T is around 5, so it's much bigger delta T. So you have, in chill beams, we have more circulating chilled water, and so we have higher consumption in pumps. And so the energy designer should be aware of this also, to input it in the model. So when we have higher chill water temperature, we have these following opportunities. We can use dedicated chillers. If you have a dedicated chiller producing water at 14 degrees Celsius, you will have a very high efficiency. You can do water-free cooling in most of the year here in Tallinn, for instance. because if you want to produce water at 14 degrees Celsius, perhaps, I don't know exactly the climate in Tallinn, but maybe 6 months per year, you can use it, do it without compressors, just using cooling tower or rat cooler, dry cooler. Also, you can use geothermal sources, seawater, lake water, whatever. And even if you don't use any of these, you just have the chiller, the normal chiller, producing water at 7 degrees for all the system, because you need a lower temperature for the primary air handling unit, because you need to dehumidify. And if you just have one chiller or two chillers that produce 7 degrees chilled water, and you have those hydraulic schemes that I showed before with the mixing valve to have a higher temperature to the beams, even so, you have a benefit in efficiency, because since the chill beams are working at a higher level of temperature, the return temperature to the chillers will be higher than with a conventional system. And if you increase the delta T to the chillers, you will increase the energy efficiency of the chillers. You can check in the literature, the published literature, there are tens of articles on the low delta T syndrome in chilled water plants that bring down the efficiency of the chiller. Of course, if the chiller works with a 5 degrees delta T, it has an efficiency. If it works with a 2 degrees, it's very often to find existing installations in which the delta T to the chillers is around 2, 2.5, and that brings the evaporating pressure down. If you have a 5 degrees delta T in the chiller, the evaporating pressure goes a little bit up. Whenever you separate condensation pressure from evaporating pressure, the compressor has to work more. It spends more energy to do the same cooling. So increasing the delta T or increasing the temperature of the return water to the chillers will increase the chiller's efficiency, even if we don't use any of those best solutions regarding energy efficiency. Also, the use of a lower hot water temperature brings the opportunity to use condensation boilers, heat pumps with a high COP temperature program, reclaim heat. For instance, I would recommend all of you that are designers to, most of the buildings today have a small data center inside the building. And this data center requires cooling year-round. And you can use reclaim heat from the data center to heat the building, or to participate in the heating of the building. In my country, in Portugal, we don't have so much heating needs, and most buildings, just using the heat from the data center is enough to heat the whole building. Okay, but when I say heat from the data center, for instance, you can have a water-to-water chiller and heat the building with the condenser energy, with the temperature of the condenser. But then you need a lower hot water temperature like the chill beams use. Again, you can use geothermal sources. And on the use of water to transport thermal energy. I will show you an example of the amount of energy that is required to supply 1000 watt cooling, either using water or air. I will not explain each step of the calculation, but as Petra said, you will receive this in PDF and you can check it. I think you can check it, everything is explained here. I've shown this several times and no one brought back to me and said, oh, there's an error there. No, I think this is correct. So, what does this show? At the end, we see that cooling with water, to cool 1000 watts, you spend 43 watts. And we are using typical pressures for the pumps, typical efficiencies. You can play with these values for your specific case. But with typical efficiency values, you will use 43 watts using water to cool 1000 watts. But with air, you need 227 watts. It's a big difference. It's around 5 times more energy using air to cool instead of water. But there is another issue, because since all this energy is used in the fan, and the fan is inside the airstream, all this energy becomes a cooling load. It's a sensible cooling load. So, remember, we are using this energy to provide 1000 watt cooling. So, with air, we are adding around 23% to the sensible cooling that we are supposed to cool at the first time. So, this is the reason why it is said that using water to cool instead of air is more energy efficient. Now, minimization of latent cooling. As I said, as you know, in beams we have no dehumidification. There are dry coils, no dehumidification. All the dehumidification is done at the central air handling unit in one place, which can be very well designed and controlled and maintained and commissioned. When you use, for instance, well, let's look at this sentence here. When we have condensation at zone coils, for instance, in a fan coil or in a DX system, no one controls dehumidification. Dehumidification of the room air is whatever. It's not controlled. And as when we have low surface coils, low surface temperature in the coils of the room, we have much higher condensation. We dehumidify much more, for instance, in DX systems that sometimes have surface temperatures of around 0. If you have a fan coil with 7 degrees, you will have around 7 to around 9 degrees of the surface temperature of the coil. If you use a DX system, you can be as low as 0 degrees in the surface. So you will condensate a lot, and it's uncontrolled and it's often excessive. Usually, when you have a DX system, people complain of low humidity. So in a beam system, dehumidification is controlled, and there's another benefit of the system. Now I have to move fast to be on time. When we do the simulation, we must make sure that all these features are taken in account. And just I would stress that you should doubt, you should not believe in the simulation. The correct attitude is to assume that the simulation is wrong until proven right. Don't believe in it. It is often wrong. There are lots of inputs, it's complex, and you should not believe it. You should analyze the results, simulate again, correct, until you feel confident that the results are correct. It's never correct on the first time, neither in the second time it's run. On DCV, I would say that recent research shows that actual occupancy of the buildings is very low compared to design occupancy. And research in Sweden and in Canada shows that average occupancy of buildings can be as low as 35%, 40% of design occupancy. So if we design primary air systems for design occupancy, most of the lifetime of the building or of this ventilation system, they will be wasting energy, delivering excessive ventilation air. So I would say that demand control ventilation, or ventilation that is changing according to occupancy, should be applied in all kinds of systems. Well, to apply it in beam systems, actually we should not just in a traditional beam just change the primary air, because if we in a conventional beam we change the primary air, we change the beam plane and pressure, we change induction, and we may not have a correct air distribution. The jet from the beam may fall to the occupied zone and create an uncomfort. Anyway, if we use a very cheap system that just relies on occupancy detectors, that when the room is not occupied, decreases the primary air to a minimum primary air, there's no issue with comfort because there's no one in the room, okay? So, and this brings already a very high economy of energy, because there are lots of times in the year in which the specific rooms may not be occupied. And there's no issue with comfort because there is no one in the room. This is simple and very cheap to implement, but doesn't use all the potential of demand control ventilation. Because actually the best would be to do this, that is to reduce the primary air to the beams when the room is occupied. If this meeting room has only 10 people, we deliver this amount of ventilation air. If we are 40 people, we deliver this bigger amount of primary air. But in order to do that, you need a more expensive system with CO2 sensors and a control loop that changes the primary air according to occupancy. Of course, to have this, you need either a VAV beam, a beam that can work correctly with changing primary air. Not all beams do it. Or you can have other strategies like a separate diffuser to supply this extra primary air that is required when the room is fully occupied. Let me check the time. Okay. On capital costs, regarding cost analysis, well, regarding the cost of installation, well, in each case should be done a comparison between beam systems with other alternatives. On regards replacement costs, we can consider 20-year lifetime for beams and other costs that are not directly related to HVAC systems. I will focus more on these other costs. Since beams use a lower amount of primary air than full air systems, we can have reduced floor-to-floor height, small mechanical rooms, and even if we have multi-service beams with lighting integrated, we may not need a suspended ceiling. These are opportunities for other costs reduction. Of course, on OPEX, operating expenditures, which is energy and maintenance, we have already talked about energy, so I will focus on maintenance. And from my experience, maintenance costs are the driving costs for the owner decision to take this solution. Because you see that with the beam system, we have no fans and motors at the room level. There are no filters at the room level, dry coils, no condensate drain pans, no condensate drain piping, and all equipments that require frequent maintenance are in technical rooms. This usually is the reason why owners go to beam systems. Energy is not the main reason. This is very important. Notice that we don't need almost to do anything at the room level. What do we need in a beam? We need to clean the coil, but since the coil is dry, it usually needs cleaning in an interval between 3 to 5 years, and cleaning is just done with a vacuum cleaner. You don't have to remove the sealing, you don't need elevation equipment, and so it's a very cheap maintenance. Of course, like in any kind of system, it's recommended to annually check the operability of the control system. Regarding sustainability, there are these issues that beam systems bring. We have an energy efficient system, minimizing energy use. We have reduced maintenance. For instance, we don't have filters at room level, so we don't have to change filters and produce material waste that we don't have all these consumable materials. We have excellent occupant comfort and long equipment lifetime, because the beams can last decades. It minimizes materials and energy use at the manufacturing stage. When we use LEED, there are these 4 credits that can be applied in beam systems: energy and atmosphere C1, optimize energy performance; environment quality C2, increased ventilation. This is more applied in the States, actually. Environment quality C71, thermal comfort and controllability of systems. Also, in renovation, since it requires very small space in mechanical rooms and low floor-to-floor height, it's a very suited solution for renovation. Even if you have a really low floor-to-floor height, you can consider even using exposed beams and avoiding at all the suspended ceiling. And also, this is important in renovation, since you don't not having to have condensate drainage piping in renovation. This is an important benefit. Also, there are existing buildings with beams, induction units. They were not called beams at the time, working for over 40 years. Actually, I'm working on 2 buildings exactly with these characteristics. Induction units working for over 40 years, and I'm sorry. And the renovation of this kind of systems is very cost effective, because we can use part of the air duct system and as a cost benefit there. Regarding humid climates, I would just stress in this final slide that you can use beam systems in humid climates as long as you do everything right. Design right, construct right, commission the system. No condensation will happen if everything is done correctly, because actually it depends on indoor air, not in outdoor air. Outdoor air condition, outdoor air is taken care in the primary air handling unit, so it turns the system independent of outdoor conditions regarding condensation. And that's it. I would just say that many of these slides were produced using past presentations from these guys from the committee, and Thank you.